Hello everybody. In this video we're going to be covering section 14.5, Polyprotic Acids. And all we're going to do in this section is extend our previously introduced equilibrium concepts to acids and bases that may donate or accept more than one proton. So we've learned a few ways of classifying acids, and we're going to have one more here. We can actually classify them by the number of protons per molecule that they can give up in a reaction. Acids that contain only one ionizable hydrogen in each molecule are called monoprotic. So a lot of our examples we've been using so far have been monoprotic. There's one hydrogen that can be donated, and it produces that hydronium and its conjugate base. An important takeaway that we have here is that not all of the hydrogens in an acid are acidic. A classic example would be like an organic acid, like this acetic acid here. Okay, these hydrogens here that are bound to carbon are not acidic. However, this hydrogen out here that's bound to this oxygen is acidic, and it is able to be donated away and produce the acetate ion. Diprotic acids contain two ionizable hydrogen atoms per molecule. The ionization of such acid occurs in two steps. The first ionization always takes place to a greater extent than the second ionization. So here we have the sulfuric acid example. It has two protons that are acidic. All right, it's able to give away the first one, and then it's able to give away the second one. All right, the conjugate base of the initial acid is able to donate a second proton. Now the Ka for this first reaction here is more than 100, whereas the Ka for this second reaction is times 10 to the negative 2. So it is 4 orders of magnitude lower for this second reaction. We can see that again here with our carbonic acid example, where we have a decreasing of 4 orders of magnitude between the first and the second ionization. Now, this leads us to an important approximation that we can make. If the first ionization constant of a weak diprotic acid is larger than the second by a factor of at least 20, it is appropriate to treat the first ionization separately and calculate the concentrations resulting from it before calculating concentrations of species resulting from subsequent ionization. So that's a bunch of words right there, right? What they're saying is that if those two Ka values are at least 20 times different from one another, which will pretty much be the case in all of our situations that we're going to have, what we can do is just treat this as if it is two problems. Okay, we can look at that first ionization, calculate all of those values, and then use the values that we calculated from that first step as the starting point for the equilibrium calculation and for the second ionization. And there are many examples in the student solution guide that show you how to go about doing that. A triprotic acid is an acid that has 3 ionizable hydrogens, and the exact same rules for diprotic acids apply. Okay, each successive ionization reaction is less extensive than the former, and this is reflected in the decreasing values for the stepwise acid ionization constants. This is a general characteristics of polyprotic acids. All right, if we had 4 acidic hydrogens, it would also follow. Okay. And typically each successive ionization constant differs by a factor of about 10 to the 5 to 10 to the 6. Here's an example with phosphoric acid that you're going to find in like cola and stuff like that. It has 3 protons, so it has 3 successive ionizations it's capable of doing. And each time the Ka value goes down significantly. Polyprotic bases. All of the concepts we've learned for polyprotic acids can be applied to bases. Okay. For instance, we have the carbonate ion. This is an example of a diprotic base. It can accept 2 protons. So first it will accept the first proton to form the bicarbonate ion, and then it will accept the second proton to form acetic acid or carbonic acid here. And if we look at their Ka, Kb values, they go down significantly from the first to the second.